Hey, well, we're back here with our series of lectures on systems of equations of linear type, that is, linear equations in multiple dimensions. I believe I told you last time that this video would have 4 parts. In fact, it's going to turn out to have 5 parts to it. The fourth part that I've just added is on Gauss-Jordan elimination with a calculator. This particular lecture is the third of our series, and it's on representing systems of linear equations with matrices, and then using the Gauss-Jordan elimination technique on those matrices to help us solve these systems of linear equations. So this is an alternative method to the previous method of using elimination to solve systems of linear equations, and in fact it's based on that method of elimination. And it was developed by the great mathematician Carl Gauss. I mentioned him earlier in relation to solving the arithmetic series sum when he was just a kindergarten kid. He grew up to become one of, if not the greatest mathematician of all times. And then later this was slightly modified by another mathematician named Jordan. So the basic idea is to streamline the notation by writing only the coefficients and constants down, and we keep track of the variables basically by keeping things lined up in a matrix, which is just a rectangular arrangement or a rectangular array of, in this case, numbers. The rows of this matrix will correspond to the equation. So for every equation that we have, we'll have a row to our matrix. And for every variable, we'll have a column of the coefficients that go with that variable. And then there'll be an extra row, extra column at the end that's a column for the constant terms. And then this matrix then represents the systems of equations. So what we're going to do then is manipulate this matrix as we would the system of equations in order to solve the system, and it allows us to not have to write down all the variables. Now, this has several advantages, and that hopefully will become apparent as we get through this series of lectures. But I will say that if you're only going to do this for a very small system, like 2 equations, 2 unknowns, or even 3 equations, 3 unknowns, I would probably just go ahead and do the previous methods we talked about if I were doing this by hand. But when you start getting to 4 equations and 4 unknowns and 5 and 6 and 7, then this method definitely is a much better. And I also want to show that there are some advantages even in smaller systems, and if you'll bear with me, I think you'll ultimately see there's one very powerful advantage that we're going to see here as we go through this. So the first thing we want to do is see how we represent a system with a matrix. So here's a system of equations, and notice how I've got it. I've got it in the form ax plus by plus cz equals d. So the constants are on the right side of the equation by themselves. The variable terms are on the left. So then equation 1 is represented by the first row there of 2, 4, -1, and -5. So I need to make sure that all my equations are written in the same order. So in this case I just chose alphabetical order, x, y, z. And so then we know that the first column represents the x's, the coefficient of the x's. The second column, the coefficient of the y's. The third, the coefficients of the z's. And finally, we have our equals. And then we have our constants on the right here. And so the second equation then is 3x minus 4y plus 3z equals 16. So in the second row, that becomes 3, -4, 3, 16. And equation 3 is then 2, 1, 0, 1. Notice we do have to put that 0 placeholder there for the 0z. So looking down here, we see the coefficients of x are 2, 3, 2. That's the first column. Coefficients of y are 4, -4, 1. That's the second column. -1, 3, 0 for the coefficients of z, third column. Then we have our equals, and then we have our constants, -5, 16, 1. Now some people will go ahead and insert a line, a little vertical line in the matrix right here, as separating basically where the equals go, separating the constants from the coefficients. This is pretty common place to do this, but there's not any real advantage of having it there. So I'm going to leave that out in the notation that we have here. So I'm not going to use this line, but you'll see a lot of people have that in the way they write these. Okay, so here's your first task, little first exercise. Take these 2 systems and write them as matrices. Okay? So you should be able to do that. Press pause now. Okay? Well, here we go. Notice they're already kind of organized the way we want them. And so then we just read off the coefficients. The first one is 0, 4, negative 1. Then we got our equals, negative 3. The next one's 3, 5, 3, 12 for the next row, and 2, 3, 7, 1 for the last row. The second set of equations is 4, 4, negative 3, 2, then 3, negative 2, 5, 0, and then 1, 4, negative 1, 5. Remember to put zeros when you're missing something. And then also remember that you might have to reorganize it so that it looks like this. So if this equation was written maybe in a different order, maybe this one was written as negative 3z plus 4y plus 4x minus 2 equals 0, you'd have to rewrite this equation in this form before you put it over here in the matrix. Alright, let's go the other direction. Take these matrices and write the system of equations that they represent. Now, of course, we have to introduce some variables. We could use x1, x2, x3 for our variables. Let's just use x, y, z here, our standard. Press pause and do this now. So if we use x, y, z and go across left to right, then this would be represented as 2x plus y plus 3z equals 5. Negative 2x plus 4y plus 7z equals 8, and negative x plus 3y plus 2z equals 7. So that system is what's represented by the first matrix. Look at the second one. The second one is particularly nice because it says 1x plus 0y plus 0z equals 3, and that just reduces to x equals 3. And the second equation is 0x plus 1y plus 0z equals 4, which reduces to y equals 4. And similarly, the last equation reduces to z equals 5. So that last one is particularly nice because it actually just has the answer right there in the last column. So if you can get the first part to look like this, where you have ones down the diagonal, we call that the major diagonal here. So 1 in the upper left, then a 1 down the diagonal like this, zeros down here in the lower triangle, a triangle of upper zeros up here, and then the answers are in the last column. So really our goal is to take a matrix that may start out looking like the first one and make it look like the last one, because our goal is to take a system that may look like this first system and turn it into a system where we just know x, y, and z. Okay, so what can we do to a matrix what can we do to this matrix to manipulate it so that our solution set each time we transform the matrix is the same, so that when we get done it will be the right answer? Well, let's think about what we can do to a system of equations. There are basically three things we can do here. One is we can switch the order of two equations. Well, I mean, that doesn't change any solution. In fact, if you're taking this example of three planes graphically, you're just changing the order you've listed them. That doesn't change anything. Well, that corresponds to swapping two rows in the matrix. So that's a legal operation. So these legal operations are called elementary row operations. So switching the order of two equations is the same as swapping two rows. So that's a row swap operation. And we'll denote that by r sub I swapped with this double arrow row sub j. So in other words, if you're going to swap row 1 and row 3, we would say r sub 1 double arrow r sub 3. So we'd swap row 1 and row 3. This is the only one of the three kinds of elementary row operations that changes more than one row. So basically, every time you do a single step in these elementary row operations, you're going to copy the matrix down, and every row is going to stay the same except one, unless you're doing a row swap, and then, of course, those two rows will change. Just change places. Now, what's something else we can do? We can multiply both sides of an equation by a non-zero constant. Well, that doesn't change that relationship. So if we have an equation that represents a plane, multiplying both sides of that equation by a constant leaves it exactly the same plane. So that certainly doesn't change our solution set. So that's certainly a legal thing that we can do. Now, of course, when we multiply both sides of an equation by a non-zero constant, if it's in the form that we have up here, you're going to distribute it across on the left, And so what's going to happen is you're basically going to multiply all those coefficients by that constant, as well as multiplying the constant term by that same constant. So what does that do for us in terms of an elementary row operation? It says we multiply each entry of the row by a non-zero constant. So if C is our non-zero constant, and we will multiply that by row I, we would denote that by CR sub I. So in other words, if you wanted to take row 3 and multiply by 4, you would write that down as 4R sub 3. And what you would actually do is take every entry in row 3 and multiply it by 4. Now so far, these two operations don't change graphically, don't change what's going on at all. The next one does change something graphically, but it keeps the same solution set. Remember, our basic elimination step is we basically add multiples of the equations together to eliminate a variable. So our elimination step is the third thing that we can do. And I can do it this way by saying it this way here. We can replace one of the equations by the sum of it and a constant multiple of another equation. So sometimes we multiply both equations by a number and added them. This time you can always think of it, especially if you allow fractions, you can always think of it as multiplying one row by a constant and adding it to the other equation. Okay? And so what this does, it replaces that plane with a new plane, but it still contains the original solution set. Okay? So, what does that do for us in terms of an elementary row operation? We add a constant multiple of one row to another row. We denote this as R sub I plus C times R sub J. And the answer is stored back in R sub I. So the first row that's listed here is the only row that's actually changing. So we're not actually changing the second row, the row J. What we're doing is we're changing the first row. But how do we do that? We take every entry in row J, multiply it by a constant, and add it to the corresponding entry in row I. So these are the only three things that we're allowed to do to our matrix. So there are three elementary row operations. Number one, swap two rows. That's a row swap. A constant multiple, multiply a row, everything in a row by a non-zero constant. And number three, add our elimination step. Add a constant multiple of one row to another row. Now notice that you can't multiply a whole row by 0. It would give you a statement that's true, 0 equals 0, but it eliminates information. So you cannot multiply by 0. Okay, so here's some examples of these. So on the left you see the original matrix, on the right you see the transformed matrix. The arrow in between says we've got a transformation occurring, and the label above the arrow tells us what transformation happened. So if you look at the first one, the label says we're going to swap rows 2 and 3. So the first thing I would do is I would recopy the row that doesn't change, row 1. So I'll recopy the first row as 1, 4, 5, 6. And then I simply switch the other two rows. The third row originally was 0, 3, 1, 2, so 0, 3, 1, 2 is the middle row or second row now. And then originally the second row was 0, 0, 7, negative 2, that's now the third row. Pretty simple concept. The next one, what I want to do is take 1/5 times row 2. So notice only row 2 is changing. This is the more typical situation where only one row changes at a time. So the first thing you do is you copy down the things that are not changing. So the first thing I do is copy down the 1, 3, negative 3, 10 for the first row, and the 0, 0, 1, negative 4 for the second row. Then I go back and figure out what needs to change, which is the second row. The third row was 0, 0, 1, negative 4. The second row now is 1/5 of the original second row. So 1/5 times 0 is still 0. 1/5 times 5 is 1. 25 times 1/5 is 5. And 7 times 1/5 is 7/5. Notice that we may introduce fractions, or I could have written it as a decimal. I could have written 1.4 there instead. However, I encourage you to mainly work with fractions rather than decimals. If your decimals are terminating decimals that terminate before too many decimal places, then decimals are just fine. If you have repeating decimals, that's more problematic because it's harder to get exact answers when you're trying to do arithmetic with repeating decimals, and writing them down's a little bit more of a pain. So you're actually better off working with fractions most of the time here. The last one is an example of our elimination step, the bottom matrix there. By the way, the word matrix is singular, matrices is plural. So we have 6 matrices on this page. We take the matrix in the bottom left and transform it into the matrix on the bottom right by the operation row 1 minus 4 times row 2. So notice that the only row is changing is the first one listed there, row 1. So recopy row 2 and row 3. Then worry about the row that changes. So here's how this works. I want to take each entry in row 2 times -4 and add it to row 1. So -4 times 0 is 0 plus 1 is 1. -4 times 1 is -4 plus 4 is 0. -4 times 7 is -28 plus 5 is -23. -4 times 2 is -8 plus 6 is -2. And actually, these 3 operations are the correct things to do at the right process at the point we're doing the Gauss-Jordan process. So these are types of things that we would need to do. And actually, if we had the matrix on the left, this is the next step. And we'll go over that a little bit more in a minute. Alright, so let's see if you can do some elementary row operations. Here's an exercise for you. So 3 exercises. I have given you 3 matrices, and now I've told you what to do to them. There's an operation of each type. Go ahead and do this transformation and see if you understand these elementary row operations. Do this now. Press pause, please. Okay, so the first thing to notice is that what changes and what doesn't change. So first notice what doesn't change. The first one is a row swap. So row 1 and 3 are changing, but row 2 stays the same. So the first thing I'm going to do is remake a matrix over here, and I'm going to copy row 2. The second one, row 2 is changing, so I'm going to recopy the matrix over here with row 1 and 3 the same and leave row 2 blank, which I'll go fill in a minute. The last one, it's row 1 is the only one changing, so I'll recopy the matrix so that the row 2 and row 3 are exactly the same. I'll leave row 1 blank and then fill it in. Okay, so now let's fill in the blanks. So on the first one, I remember I said I was going to recopy row 2, so it's just exactly the same. And what was down here in row 3 is now in row 1. And what was up in row 1 is now down in row 3. The second one, I leave row 1 and row 3 alone, and I multiply row 2 by 1/3. 1/3 times 0 is 0. 1/3 times 3 is 1. 1/3 times 15 is 5. And 7 times the 1/3 is 7/3. And the last one, I need to do an elimination step. That's a more complicated one to do. Okay, and notice only row 1 is changing. So what do we do first? Well, we copy row 2 and row 3. And so we see that I've done that so that they're exactly the same. Now how do I change row 1? I take everything that's in row 2, multiply it by -3, and add it to the corresponding entry in row 1. And the answer goes back in row 1. So let's do this. -3 times 0 is 0 plus 1 is 1. -3 times 1 is -3 plus 3 is 0. And -3 times 5 is -15 plus 3 is -12. -3 times 7 is -21 plus 5 equals -16. Hopefully this is what you got when you worked it a minute ago. Alright, here are some operations that have been done, okay, and see if you can just write down the label for what happened here. So the work of manipulating the matrix has already been happened. Just see if you can write the description. It's going to be very important as we're working through these that we communicate. Part of mathematics is learning how to communicate the process of what we've done. And so labeling these things carefully is going to help us understand what's going on when somebody looks back at this. Otherwise, you can just see a bunch of numbers that can kind of glaze over when you see too many of these at once, but the labels help you a lot. So go ahead and do this exercise now. Write down the 3 labels for these 3 different transformations. Press pause now. Well, let's look here and see what we've got. In the first one, notice it's row 2 and 3 I've left alone, so the change has happened in row 1. So it's not a row swap, and the first number stayed the same, so it's not just multiplying by constant. We must have used our elimination step. And let's see if what we've done here. Multiplying the row 2 by 0 and adding to 1 would stay the same. Same way down here. What about this? If we multiply this one by 0 and add it to row 1, that would stay a 4. Well, it didn't, so I must have been using row 2 somehow. So I got a 0 here. That must have meant I multiplied this by -4 and added to that. Okay, so let's keep going here. Let's see if this works. -4 times 0 plus 1 is 0. -4 times 1 is -4 plus 4 is 0. -4 times 5 is -20 plus 3 is -17. -4 times 7 is -28 plus 5 is -23. Okay, good. So that's it. So what we did is we took row 1 minus 4 times row 2. Alright, what about this one here? Let's see what didn't change and what did change. Okay, the first one stayed the same. Oh, looks like we got 2 rows changing where they swapped. So this is just a swap of row 2 and row 3. So it's row 2 swap with row 3. The last one, the first row and the second row stayed the same. It's the third row that changed. And if you look, I believe we just multiplied that row 3 by 1/4. Okay, so check that out. 1/4 times 0 is 0, 1/4 times 0 is 0, 1/4 times 4 is 1, 1/4 times 8 is 2. And so there are your labels. So the first one we did row 1 minus 4 times row 2. That was the elimination step. And what we did, notice we eliminated the y term, if this is x, y, z constants. Okay, we eliminated that 4y from the first one. So that was an elimination step. This one down here, when we swap 2 rows, we're just swapping the second and third row. We're just swapping the order of the equations. And this one down here, when we multiply the last row by 1/4, we've got basically 4z equals 8. Now we have 1z equals 2. So we just solve that last equation for z by dividing both sides by 4. Alright, so now let's start talking about the Gauss-Jordan elimination technique. So the basic idea of the Gauss-Jordan technique for solving systems of linear equations is to do the following. We want to represent the equations as a matrix of coefficients augmented by a constant column. We want to manipulate the matrix with a series of elementary row operations. And again, what are those row operations? We could swap 2 rows, row sub I, double arrow, row j, swapping row I and j. We can multiply each entry in a row by a non-zero constant, c times row I. And we can add a constant multiple of one row to another row, row I plus the constant times row j, and the implication there is that's stored back in row I, which is the only one changed. Now what we're trying to get is a matrix that looks like the following. It could have, this could have 2 or 3 or 4 or 5 different rows depending on how many equations you have, and the columns depend on how many variables you have. But what we like is one's going down this diagonal, however many rows we have, with zeros in the lower triangle, zeros in the upper triangle. If we get that, then whatever you have in this last column, that's exactly your answer. That's your x, y, z, whatever, or x1, x2, x3, x4, whatever. Those are your coordinates of that answer. Now, you can actually get this to happen if, in fact, a unique solution exists. We've already seen examples in the earlier videos where we don't always have a unique solution, and what you can always get is a matrix that is in reduced row echelon form. This is reduced row echelon form, but there are some other possibilities for that. We'll talk about that in the next slide, but when you got it in reduced row echelon form, we can generate the answer from that, whether it's one answer, no answer at all, or infinitely many answers. Okay, so basically the goal of Gauss-Jordan manipulation then is to get the matrix in what's called reduced row echelon form, or RREF for short. And so then we can use the RREF matrix, the reduced row echelon form matrix, to write down the solution to the system of equations. So a matrix is in this reduced row echelon form if and only if it meets all the following criteria. First of all, you have leading ones. In any row, the first non-zero entry from the left is 1. So notice in all these examples down here are in reduced row echelon form. Every row, it could have some zeros at the beginning, but the first number you come to from the left that's not a 0 has to be a 1. Okay, so notice that's true here, 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 here. Now you could have a whole row of zeros, that's okay too. That doesn't violate the leading one thing because it just doesn't have any things that's non-zero. But if it has anything that's non-zero at all, the first one you come to has to be a 1. And we can always get that to happen. If it's not a 1 there, you can just multiply by its reciprocal if it's not 0. Now, zeros. We got a lot of zeros. And anytime you have a leading 1, then anything below it or above it must be a 0. So anything below this 1 is a 0. Anything above or below this 1 is a 0. Above that 1's a 0. 0, 0, 0. Zeros here, 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 down here. Okay? And of course, leading ones, could do this. Now, the order of the rows. Any leading 1 is always to the right of any leading 1 in a row above it. So I have a leading 1 here. I cannot have a leading 1 right below it. I should be able to eliminate that using elimination step and get a 0. So the leading 1 has to be to the right, which is here. And then the leading 1, next one, is to the right. So ideally, they're down a diagonal here. You can get a situation like this one where you get a leading 1 here and here, and then it just so happens that the next leading 1 kind of skips over 1, so it goes to over here, 1 here. Okay? Leading 1's here and here, nothing. So each time you go down a row, the leading 1 goes 1 or more places to the right. You never have leading 1s on top of each other or going back to the left. And if you do have any rows that are completely zeros, like these last two examples, they have to be at the bottom of your matrix. You could even have a couple of rows that are completely zero. They're the bottom two rows then. Okay, so this is reduced row echelon form. And so our idea of the Gauss-Jordan technique is to get it in this form. So let's look at an example. So we're going to solve this system of equations using the Gauss-Jordan technique. Okay, first step, we're going to write this as a matrix. There we go. Check it out. 0x plus 4y minus 1z equals 5. 0, 4, 1, negative 1, 5. 3x plus 5y plus 3z equals 2. That's 3, 5, 3, 2. 2x plus 3y plus 7z equals negative 4. 2, 3, 7, negative 4. Over here, 2, 3, 7, negative 4. So there is our matrix. 3 equations, 3 unknowns. There's a possibility we could get a unique solution to this. Alright, the next thing we want to do is we want to get a 1 right here in the upper corner. Now, if this was not 1, we could just multiply by its reciprocal. But being a 0, 0 doesn't have a reciprocal. So we're going to have, that's when you need to do a row swap. So find one of the rows below it and swap. I can either swap it with the third one or the second one. So I actually swapped it with the third one. And then I've got a non-zero entry there. I can divide the first row by 2 or multiply the first row by half, and that gets me my 1 where I'm after it. So my first goal is to get a 1 in the upper left corner. If it's not a 1 already, if it's a 1 already, mission accomplished, go to the next goal. If it's not a 1 already, then if it's a non-zero number, we just multiply by its reciprocal, but then you have to multiply the whole row by the reciprocal, and that's what I did going from here to here. If it's not already a non-zero, like if it's a 0 there, find a non-zero one below it and swap. And I have a choice of, I could swap with either the second or the third row with the first one. And so mission accomplished, we have a 1 in the upper left corner. Next mission, get zeros below it. Now here we have a bonus because we already have one of these is already zeroed out. We need to zero out this one. To do a zero out something, we have to use our elimination step. Since we worked hard to get this to be a 1, it's pretty easy to see what to do, I think. What is it? Well, we're going to multiply row 1 by -3 and add to row 2, and that's going to eliminate this. So row 2 minus 3 times row 1. Let's check it out. So the answer, first of all, notice that the only thing that's changing is row 2. So I'm going to copy row 1 and row 3. To change row 2, I'm going to multiply everything in row 1 by -3 and add it to row 2. Notice this does not actually change row 1, it only changes row 2. Okay, so here we go. -3 times 1 is -3 plus 3 is 0. That's what we were trying to do, is get a 0 there. Alright, -3 times 3 halves is -9 halves plus 5. 5 is 10 halves. -9 halves plus 10 halves is 1 half. Okay, that's good. -3 times 7 halves, let's see, that's -21 halves plus 3. 3 is 6 halves. -21 halves plus 6 halves is -15 halves. And then -3 times -2 is +6 plus 2 is 8. Mission accomplished. We obtained a 0 there by one of our legal means, by one of those allowable row operations. Namely the type 3 elimination type. Now what's next? Well, we want to go down the diagonal next and get our 1. So basically get a 1 here. Every time you get a leading 1, clear out zeros below it. Okay? And get the lower triangle of zeros down here. You can clear out zeros above it if you want, but the main thing is I usually get the zeros below first. So we want to get a 1 right here. Now sometimes you can combine these rows somehow to get there using an elimination step, but we can usually what we're going to do is just simply multiply by the reciprocal here. So the reciprocal of 1/2 is 2, so we'll just double this row. This will give us a 1 there where we need it. I'll have the added bonus of getting rid of this other fraction as well. So we just multiply row 2 by 2. Notice that leaves row 1 and row 3 alone, so the first thing I do is copy those. Multiply everything in row 2 by 2. 2 times 0 is 0. We don't want to mess that up. Whatever we do, we don't want to mess up these 2 zeros and this 1, or this 1, or we're trying to get this 1. We don't want to mess up these 2 zeros and this 1 because we worked hard to get that. Okay? But this will be just fine because notice 2 times 0 is still 0. Multiplying a row by a constant does not change a 0. So 2 times 1/2 is 1. That's just what we wanted. But of course you have to multiply the whole row by 2. 2 times 0 is 0. 2 times 1/2 is 1. 2 times -15 halves is -15, and 2 times 8 is 16. Next we've just got a leading 1, so now we want to clear zeros below it. We want to get rid of that 4. How will we do that? Well, I can make use of this leading 1 that I just got. So for example, if I try to use this one right here and try to do some sort of elimination using row 1, I could probably get that to be a 0, but it's going to mess up this 0, which we really want because there's a 1 here. But notice these are both zeros here, so using elimination step with row 2 is not going to change that 0. In fact, what are we going to do? We're going to multiply by -4 here and add. So -4 times 1 is -4 plus 4 is 0. -4 times 0 is 0 plus 0 is 0. So it's not going to mess up our 0. It will turn the 4 into a 0, and then it'll affect these other numbers as well. Let's check it out. So notice it's actually row 3 that's changing. So notice I copied row 1 and row 2. And I multiply -4 times row 2 and add it to row 3. So -4 times 0 is 0 plus 0 is 0. -4 times 1 is -4 plus 4 is 0. Mission accomplished. We got a 0 here without messing up our 0 here. Now let's finish the rest. Negative 4 times negative 15 is positive 60, plus negative 1 is 59. Negative 4 times 16 is negative 64, plus 5 is negative 59. So 1 in the upper left, get zeros below. Come down the diagonal, get a 1, 0 below. Come down the diagonal, we want that 59 to be a 1. How are we going to do that? Yeah, just multiply by 1/59th, or divide by 59. So we would take row 3 and multiply by 1/59th. Notice again, the first thing I do is recopy my first and second rows. It's only the third row that changes. 1/59th times 0 is 0 in both places here. 59 times 1/59th is 1, and negative 59 times 1/59th is negative 1. So now we actually know that z equals negative 1. Now actually when Carl Gauss did this, he stopped at this point. And if you stop here, it's just called Gaussian elimination. And we could do back substitution because we know z is negative 1. Here's an equation that just has y and z. We could substitute z back into there and solve. And then once we had y and z, we could substitute into this equation that has x, y, and z to solve for x. And that would be called Gaussian elimination with back substitution. But if you're going to go to the trouble of setting up the matrix, you might as well just keep going and do the Gauss-Jordan technique, which is to get this all the way into the reduced row echelon form. Okay? Technically, this matrix is called row echelon form, but not reduced row echelon form. So let's keep going. Well, the only thing left to do is to clear out zeros above these leading ones. So we need that 3 halves, the 7 halves, and the negative 15 to turn into zeros. And you can actually do those in any order that you want. I usually start here and kind of go across the first row and then down. But you can go really in any order that you think is convenient. Okay, for those last zeros. So I'm going to multiply this by negative 3 halves times row 2 and add that to row 1. Okay, and so that's the step right here. So negative 3 halves times 0 is 0 plus 1 is 1. Notice it can't mess up that 1. That would be bad. But since we already have a 0 here, it's not going to mess up the 1 above. And so negative 3 halves times 1 is negative 3 halves plus 3 halves is 0, what we need. Negative 3 halves times negative 15 is positive 15 halves. Let's see. No, wait a minute. Positive 45 halves plus 7 halves. That's 45. That's 52 halves, which is 26. Okay, so that's 26 there. Negative 3 halves times 16. 16 divided by 2 is 8 times negative 3 is negative 24 minus 2 more is negative 26. Now I'm going to get rid of the 26 here by multiplying row 3 by negative 26 and adding the result to row 1. So I'm leaving row 2 and row 3 alone. Negative 26 times 0 is 0 plus 1 is 1. Negative 26 times 0 is 0 plus 0 is 0. Negative 26 times 1 is negative 26 plus 26 is 0. So mission accomplished. We got a 0 where we wanted it, and we didn't mess up the other stuff that we tried to get so hard earlier. Finally, negative 26 times negative 1 is 26 plus negative 26 is 0. So now we know x is 0 and z is negative 1. Finally, we'll find y by adding 15 times row 3 back to row 2. And so you can see the last step there. 15 times 0 is 0 plus 0 is 0. 15 times 0 is 0 plus 1 is 1. 15 times 1 is 15 plus negative 15 is 0. 15 times negative 1 is negative 15 plus 16 is 1. And notice we have exactly what we want. And now we can write down our final answer. The first equation says x equals 1. Next one says y equals 1. X equals 0, excuse me. Y equals 1 and z equals negative 1. So our equation, system of equations, has a solution of x, y, z, the order triple, equals 0, 1, negative 1. Now you definitely want to check this because let me tell you, there is a lot of arithmetic going on here. Lots and lots and lots of arithmetic problems. None of them are very hard, but there's just lots of them to do. And it's very, very easy to lose your concentration for a minute and make a careless error. So be sure that you check your answers. Not hard to do by hand. Let's just check them by hand here. The first one, x is 0, y is 1, z is negative 1. So we have 4 times 1 minus 1 times negative 1. That's 4 plus 1 is 5. 5 equals 5, so it checks. The next one, 0 is for the x, so it goes away. 5 times 1 plus 3 times negative 1, that's 5 minus 3 is 2, that checks. Check the third one, the 0 knocks out the first term. 3 times 1 is 3, plus 7 times negative 1 is 3, minus 7, which is negative 4. Here's a calculator check down here. If you have your calculator handy, you can do it this way. 0 stores x, hit enter, that's 0. 1 stores y, hit enter, that's 1. And by the way, y is like alpha, one of the number keys to get the y. And then negative 1 stores z. Again, alpha something for z. That's negative 1. Then I just cleared the screen and type my left side of my equation, and I should get the right side of the equation for the answer. With those values of x, y, and z, if I do 4y minus z, I get 5, which is what it's supposed to be. 3x plus 5y plus 3z is 2, so that says that point is on the first one, and then on the second equation. And then we try it again on the third equation, 2x plus 3y plus 7z, and sure enough, that's negative 4, so it checks in all three equations. So we feel really good. We've got us a good solution here. So that is Gauss-Jordan elimination. Now, as I said earlier, if I'm going to do this with two equations, two unknowns, I'm probably not going to write it in a matrix like this. I might, but probably not. Three equations, three unknowns, well, sometimes I might want to write it with this way, but it's about as easy to do just the elimination methods we learned earlier. Okay? But if you get four equations or more, then this matrix method definitely makes it more worthwhile. Alright, so let's talk some more about generalities of what we're talking about here. So in Gauss-Jordan elimination, we can use any combination of elementary row operations as long as they're leading us to our goal of getting the matrix in reduced row echelon form. Now remember, we're just trying to get ones and zeros in certain places or certain entries in our matrix. So you want to be sure that when you work hard to get a 0 or a 1 somewhere, you don't come along and mess it up later on with a different step. Okay, so you definitely don't want to get like a dog chasing his tail where you're going around in circles and circles and circles and not getting anywhere. So, and that can happen to you if you make some poor choices of what operations to use, where you keep messing up the stuff that you worked hard to get earlier. So be sure that once you work hard to get a 1 or a 0 in a certain place, that you don't go back and mess that up later on. Okay, so how do you get a 1 somewhere? Well, sometimes there's different things that you can do. Sometimes if there's a 1 down below it, you can just swap a row. Or sometimes you can use an elimination type step. Usually if you really eliminate something, it's a 0. But sometimes you can use that type of operation. But as long as it doesn't mess up earlier work. But the thing you usually want to do is the basic thing to get a 1 is just multiply by the non-zero constant. So you want to multiply by the reciprocal of whatever it is you want to turn into a 1. If you do that, it only changes that one row, and notice multiplying by a non-zero number leaves zeros zeros. So it's not going to change a 0 into anything else. It's going to leave zeros alone. Whereas if you try to apply that elimination type operation, it may change a 0 into something else, which is going to mess up what you did earlier. That's not good. Now, anytime you see it's useful to do a row swap, you're welcome to do that. But it's especially used when we want a 1 somewhere, and the thing that's already there is a 0. Well, you can't do that step of multiplying by its reciprocal because 0 doesn't have a reciprocal. So what you need to do is look down below that 0 and see if you can find something that's not 0. Then you can swap the rows, and then you can go ahead and multiply by reciprocal. Okay? Now, if you want to zero out something in a cell, you basically need to apply your elimination operation. Now, remember, you cannot multiply by 0 all the way across. So you can't. That's not an option. So what you're going to have to do is basically use that elimination steps. If you see one you might work for you to just swap, sometimes that is helpful, but most of the time you're going to get a 0 by the elimination operation. So the cell that you're wanting to be a 0, basically you want to multiply something else, probably a 1, If you got another row that's got a 1 first, that's why I got the 1s first, leading 1s, you can multiply that leading 1 row, that row with the leading 1 in the same column, by the opposite of the number you're trying to zero out, add it to the row you're trying to change, and that will give you 0 where you need it. Now, if you practice this enough, you can develop some skills in choosing operations so as to make the arithmetic here easier. So, for example, sometimes if you're clever in the way you make your choices, you can avoid fractions. Maybe not completely, but put off the numbers being fractions. So if you're kind of clever in what kind of operations you do, sometimes you can make the arithmetic easier on you. Sometimes by adding a step to it, sometimes by making something into 2 steps, rather where you could have done it with 1 to get your goal accomplished. By making it 2 steps, you make the arithmetic a lot easier. This is a little hard to teach this skill. It's more of a matter of just a feel for it you get for working with the numbers as you practice it. But it turns out there is actually a specific order that you can always use. So there's basically a basic algorithm that you can apply, that you have to do the steps, or you can do the steps in the specific order. Let's take a look at what that would be. So of course you start by representing the system with a matrix. Your first goal is to get a 1 in the upper left corner. Now notice, by the way, you'll never have a whole column of zeros. What would that mean? Well, you might have the constants all be zeros, but you'll never have a whole column of zeros where the variables, where their coefficients, because if all the coefficients of the, say, the x's are zeros, why do you have an x in there to begin with? Because there's no point. So you'll never have a whole column of zeros. So if the entry is already a 1 where you want it, good. Goal 1's accomplished, check it off, go to the next step. Nothing to do. If it's a non-zero number and you want it to be a 1, just multiply that whole row by its reciprocal. The reciprocal of the entry you want to change. That'll turn that non-zero number into a 1. Of course, it'll change the other numbers in the row too. Could even introduce fractions or decimals, but hey, we just got to deal with that. Okay? Now, you can't do that if the number is a 0. So what you can do, since the whole column is not 0, somewhere down below it there's a number that's not a 0. So go find the one below it that's not a 0 and move that up by a row swap, and then multiply by reciprocal and turn it into a 1. Now that gets you a leading 1. Now once you have a leading 1, then you want to get zeros all the way down below it. And we can use this new 1 that we just got in a very, very systematic and easy way to get zeros below it. What we do is say we want to, say the second row, we want to turn the first entry in the second row into a 0. We want to eliminate that variable, basically. We just find the opposite of that variable, of that thing we want to eliminate, multiply that number by, in other words, the opposite of the one we're going to get rid of, take that number times the row with the leading 1, add it to the row that we want eliminated, or the row that has the thing we want eliminated, and that'll get you a 0 where you're wanting it. And do this for each of the rows below that leading 1. Now you basically just go through a loop going down these things, going through these steps again and again. So once you got a 1 in the upper left corner, you 0 out below it. Then you move down the diagonal to put a 1 there. Now it could be that you got all zeros from that point on. If you do, then you have to just go to the right, keep going to the right one until you get something that's non-zero, or a column that's non-zero from there on down. Okay? Then you get a 1 in that leading position. How do you do it? Well, same way we just talked about. Multiply by the reciprocal. If it's a non-zero number, if it's a 0 number, look below it and find a row to swap up. And then continue like that. And you just keep doing this, moving sort of down and to the right until you get to the bottom of the matrix. And then you've got a leading 1 in each row with them kind of going down and to the right each time. And to the left of them, of course, now are all zeros. So you got this sort of a triangle or area down in the lower left that's all your zeros, Your ones are kind of down the diagonal or close to it. And then the next step is to zero up above the leading ones using your elimination step, and then then at that point you've got it in the form that you want. All right, so this one here has been done with the steps in that order. Okay, and what I'd like you to do is to go through and label the steps here. So we should, this is not, wouldn't be good to turn in for a grade because the labels aren't there. So we need to go ahead and provide those labels. Okay, so watch what's going on here. Provide the labels for an exercise. Go ahead and do that now. Press pause. All right. Well, our first step is to get a 1 in the upper left corner. Okay, that's a 0 element, so we need to swap out. I just swapped it with the row below. So I left row 3 alone, and I swapped row 1 and 2. Next, I get a 1 right there in the upper left by multiplying by its reciprocal. So I need to multiply by 1/2. Of course, I have to multiply the whole row by 1/2, which leaves row 2 and 3 alone, but takes 1/2 times everything in row 1. So 2 times 1/2 is 1, 4 times 1/2 is 2, 8 times 1/2 is 4, and 34 times 1/2 is 17. Next, I want to get zeros below that leading 1. Once I get a leading 1, 0 out below it. Hey, bonus! We already got a 0 here, so that's one step we don't have to do. But we do need to get that 3 into a 0. Multiply row 1 by its opposite. So take -3 times row 1 and add it to row 3. Notice again, this leaves row 1 and 2 alone, and it's only row 3 that's actually changing. -3 times row 1 is -3 times 1 is -3 plus 3 is 0. That's what we were after. -3 times 2 is -6 plus 6 is 0. That's another little bonus there. -3 times 4 is -12 plus 9 is -3. And -3 times 17, -51 plus 42 is -9. Next we go down. So we got it. What have we done? We got a 1 in the upper left, 0's below it. Now we get a 1. We go down the second row and make its first entry a 1 down the diagonal. So move over to the second column and we get a 1 here. Well, it's non-zero, so I can just multiply by its reciprocal. Multiply by 1/5. Now in this particular case, all of the numbers turned out to be nice terminating decimals, so I used decimals instead of fractions. Most of the time you want to go ahead and just use fractions instead. But notice here again, row 1 and row 3 are left alone, and I multiply row 2 by 1/5. 0 times 1/5 is 0. 5 times 1/5 is 1. That's what we were wanting. 2 times 1/5 is 2/5, or 0.4. 16 times 1/5 is 16/5, or 3.2. Okay, that's it. Then we want to get a 0 below that. Next step. Well, it's done for us, so there's a step we can just check off. Normally this would be another step here. Next we go down the diagonal to here, get a 1 here. Well, it's non-zero, so we can just multiply by its reciprocal. Multiply row 3 by -1/3. Notice it leaves row 1 and row 2 alone. Multiply row 3 by -1/3. -1/3 times 0 is 0 in these first two cases. -1/3 times -3 is 1, as we wanted. What does that do to the rest? -9 times -1/3 is 3. So now we know z is 3. Now we go back and get zeros up above. And really you can do these last three things up here. This 2, 4, and this 0.4 need to become zeros. And you can really do those in any order that you feel is good for you. Okay? I usually just start, if I don't have any other preference, I start here and do this one here, the top. Then I do the next one at the top and then down below it, and the next one below it until I run out of stuff. Okay, this one I only have 3 things to turn into zeros. So I want to turn that 2 into 0. I use the leading 1 in its column, so I'm going to use row 2 to do it. So I'm going to take row 1 minus 2 times row 2. So I'll leave row 3 and row 2 and row 3 alone, so I recopy those, and then I change row 1. Notice that -2 times 0 is 0 plus 1 is 1, so this is good news. I did not mess up that 1 that I had earlier. If I tried to make this a 0 earlier on, I probably would have messed up my 1. So I need to wait until I get my zeros over here. Now, where am I? Okay, so I want to multiply -2 times row 2 plus row 1. -2 times 0 is 0 plus 1 is 1. -2 times 1 is -2 plus 2 is 0. That's what we were trying to get accomplished. Let's see what else happens. -2 times 0.4 is -0.8 plus 4 is 3.2. Negative 2 times 3.2 is negative 6.4, plus 17 is 10.6. Now we want to clear out a 0, and these two, I chose to do the 3.2 first. So multiply, don't use row 2, because if I use row 2, I could figure out something to zero that out, but it'd mess up this 0 that I have here. So I want to use row 3. I want to use the one that has a leading 1 in that column. And so we're going to multiply row 3 by negative 3.2 and add to row 1. So row 2 and row 3 are left alone. In fact, row 3 is done. It's not going to change for the whole rest of the thing. So row 1 is going to be done after this step. Negative 3.2 times 0 is 0, plus 1 is 1. Negative 3.2 times 0 is 0, plus 0 is 0. Good. It doesn't mess up our zeros. Negative 3.2 times 1 is negative 3.2, plus 3.2 is 0. Good again. That's what we were trying to do. And now let's see what happens here. Negative 3.2 times 3 is negative 9.6, plus 10 is 1. So now we know x is 1 and z is 3. Now we just have one more thing to do, and that's to get the this last 0.4 into a 0. So multiply row 3 by negative 0.4 and add up to row 2. So row 1 and row 3 are left alone. Row 2 is changed by multiplying row 3 by negative 0.4 and adding to row 2. Answer is in row 2. Negative 0.4 times 0 is 0, plus 0 is 0. Negative 0.4 times 0 is 0, plus 1 is 1. Negative 0.4 times 1 is negative 0.4, plus 0.4 is 0, as we need it. Negative 0.4 times 3, that's negative 1.2, plus 3.2 is 2. And so now we can see our final answer is xyz equals 1, 2, 3. Now we definitely want to check this, so be sure you check your solutions. Here I did the check by hand. The first one is 5 times y plus 2 times z equals 16. Put in y is 2 and z is 3. We get 5 times 2 plus 2 times 3 equals 16. 5 times 2 is 10. 2 times 3 is 6. 10 plus 6 is 16. 16 equals 16. It checks. So that point is on the plane represented by 5y plus 2z equals 16. It satisfies that equation. Check it in the second equation. 2x plus 4y plus 8z equals 34. X is 1, y is 2, z is 3. Work this out. 2 times 1 is 2, 4 times 2 is 8, 3 times 8 is 24, 2 plus 8 is 10, plus 24 is 34, 34 equals 34, that checks. Similarly, check 3x plus 6y plus 9z equals 42, when x is 1, y is 2, z is 3. Plug in 1 for x, 2 for y, 3 for z, in parentheses. 3 times 1 is 3, 6 times 2 is 12, and 9 times 3 is 27, and add those up. Let me do it in this order. 27 plus 3 is 30, plus 12 more is 42. 42 equals 42. It does check. So easy enough to do the check by hand. In fact, it's a lot easier to check it than it is to work it out. So definitely do not skip the check. So if you have to do this by hand, you can check them like this pretty easily. If you've got your calculator and you want to check it, then you can do it like this. 1 stores x, 2 stores y, 3 stores z, and then just type in the left side of the equation, and the output should be the right side of the equation. Notice that 5y plus 2z is 16, 2x plus 4y plus 8z equals 34, and 3x plus 6y equals 9z is 42, as we need it to be with those particular x, y, and z. So the x, y, z equals 1, 2, 3 is the correct solution. It does check. Alright, so next we're going to have an exercise, and this one we're going to actually review what we did in the earlier videos, the last couple of videos in this series, as well as the Gauss-Jordan technique on this particular one. So we're going to start with the system of 2 equations and 2 unknowns, and I want you to do it with all of these different methods for practice. The intersection of Graph's method using Graphmatica, the intersection of Graph's method using your calculator, the elimination technique, the substitution technique, and the Gauss-Jordan elimination method. So you solve this using all 5 of these methods, and of course they should all agree with each other. Go ahead and do this now. Press pause and come back when you're ready. Press pause now. So here in Graphmatica, in the little box up here, I just typed these in just like they look. The first I typed in 4x minus 5y equals 15. Enter, and that gave me the red equation. And then you can see where I typed it in here, 3x plus 6y equals 9. Enter, and that gives me the blue equation. They clearly cross in one spot. If I need to, I might manipulate the window a little bit. Up at the top, there's a menu right in this vicinity that says Tools. Click on that. Then about the second or third one down that says Find Intersection. This dialog box pops up. It tells me my two equations I can pull from my drop-down menus here. And if it's showing on the screen, I'm in good shape. Just hit Calculate. And it will give me approximations of the solution. Now, these are not actually the correct solutions. These are the correct solutions in decimal form rounded off to 4 decimal places. So actually, these are not actually the exact answers, but they are approximations. Now, this is probably the easiest method to use if you have Graphmatica available for one of these, because you don't have to do any solving by hand. You simply type the things in just like they look. You just have to choose Tools and Find Intersection and Calculate. Just to click on a couple buttons, and boom, it gives you the answer. Now, if it's a real-world problem, maybe you're going to be rounding off to 4 decimal places or less anyway. This will give you a perfectly fine answer, and you can just go with that. If we're trying to find an exact solution, this is not exactly right. In fact, if you try this, store this number as x and this one as y, and then do 4x minus 5y, you're not going to get exactly 15. You'll get real close to 15, but not exactly. Now, in the calculator, we can actually get an exact value for this, but we have to do a little manipulation first. To get it in the graphing window on the calculator, we first have to solve for y, both equations. So the one that was graphed in red on the last graph is the 4x minus 5y equals 15. Let's see, add negative 4x to both sides, then divide both sides by negative 5. We get y equals 4/5 x minus 3. The one that was in blue on the previous graph was 3x plus 6y equals 9. Let's see, subtract 3x from both sides and divide both sides by 6. I distributed that and simplified the fractions to get y equals negative 1/2 x plus 3/2. So now we have them in the form that we can put them in our calculator, y equals something. So you hit the y equals button in the way upper left-hand corner of a TI-84, and you type in your equations, 4/5 x minus 3, and then negative 1/2 x plus 3/2. Notice I did put my fractions in parentheses. Actually, on an 83, this probably works okay. On an 84, it's not going to give you the right thing if you don't put the on an 82, it's not going to give you the right thing if you don't put the parentheses in. 83 and 84, it might be okay, but it's probably better to get in the habit of just putting those whole parentheses around the whole fraction. So anyway, we do that. I just did a zoom standard, which is this window that you see here, and got a graph, which is this graph that you see down here in the lower left without all the numbers. And we can see the point of intersection on that window. If we couldn't, we would need to look at the way the graphs are slanted and maybe somehow figure out a better window. Then once we found our reasonable window, we do calculate, intersect. So this will compute the intersection of the two graphs. Now remember, calculate is second trace, second button, and trace is way up the top. And choose number 5. So you can go second trace and then just hit number 5, or move the arrow down to the 5 and hit enter. It's going to ask you for curve 1 and curve 2. If you only have 2 curves, you hit enter, enter, and then it's going to ask you for a guess, so put the cursor kind of close to where they cross, hit enter, and it's going to give you an x and y. Now again, these are decimal approximations, okay? But if I go to the home screen and ask it to write these in fraction form, it's going to give me an exact fractional answer. So I can get to the home screen, as long as I do this right after I've done the calculate here, the x and y will be the x and y values on the screen. In fact, if I just typed x and enter, without the change to fraction, it would return 3.461538, and it might give me a 4-6 something instead of rounding off to 5. It may give me a couple more digits. Okay? but you'll basically get the same x, and if you did alpha y and enter, you get the same y. But I don't want it that way. I want it in fraction form, so I say x, change to fraction. Again, this change to fraction is under the math menu, and it's this is on a T84 at least. It's under the math menu, and it's just math, and then it's the first thing. So just hit math, enter, and then enter one more time, and you get 45/13. And similarly, you do alpha y, so it's alpha button, and then y is like something down near the bottom, like 1 or 2 or something. And you hit that, and change to fraction again. Again, math, enter, enter, and it comes out with -3/13. So now we have an exact value in fraction form. xy is equal to 45/13 comma -3/13. In an exact decimal form for this is a repeating decimal, and if you divide this out using long division, you'll find a repeating pattern, but only after you've reached a 6-digit pattern here, which is actually kind of good news, because with the denominator 13, you could have potentially you can go up to one less than the size of the denominator is how many might be in the repeating pattern. In this case, we got lucky. It didn't go all the way out 12 times before it started repeating. It only went out 6. And so it turns out to be 3.461538, and then again 461538, 461538, 461538. So the 461538 is repeating. Likewise, the -3/13 is -0.230769, with the 230769 all repeating. Okay, so I mean, if you're wanting exact, actually this is not approximate equal, this is exactly equal to, because it's repeating decimal. Okay, but if you're going to do these, I would probably, if you'd want exact answers, you're probably looking for fractions here. So when you do these on the homework, my math lab, it's probably, if it asks for exact answers, they're probably looking for, if it's not an integer, they're looking for a fraction. So use the little fraction palette on the left to enter your answers there. Alright, how about the same equation by substitution? Pick one of the equations and solve for y. We've already seen this. Take the red one, 4x minus 5y equals 15. Solve for y. Y is 4/5 x minus 3. And put that 4/5 x minus 3, put that expression that y is equal to in place of y in the other equation. The other equation, the blue one there, is 3x plus 6y equals 9. And notice where the y was, I put what y is equal to in the other equation, the 4/5 x minus 3. Be sure you don't substitute back into the same equation, because that will just give you something true like 0 equals 0, 1 equals 1, or so forth. Now we have one equation, one unknown now at this point, the equation that's got the blue and the red together, and now we can solve that equation. So I'm going to do the distributive property. So we still got the 3x and the equals 9 that don't change, and then we got 6 times -3 is -18, and 6 times 4/5 x is going to be 24/5 x. Multiply both sides of that equation by 5 is one way we can do that to clear out fractions. Distribute on the left, we get 15x plus 24x minus 9 equals 45. There is a typo here in copying. Let's see here. That's still plus, and it's but I fixed it back here. It's still plus here. Okay, so we're still good. Multiplying by 5 clears that denominator out there, and then gives us this. Combine like terms, and then add 90 to both sides, and then divide by 39. It's 135 over 39, which reduces to 45 over 13. Same as we got before, so that's good news. So now we know x is 45 over 13. Go back to the equation that's got y's and x in it. Plug that in place of x. Solve this equation down. 45 divided by 5 is 9. 9 times 4 is 36 over 13. Multiply top and bottom by 13 here to get 39/13 for 3. Subtract here, we get -3/13, and that's y. How about elimination? Okay, If I were doing this by hand, this might be the way I might do it. So we can eliminate the y's by multiplying the first equation by 6 and the second one by 5. So that gives us 24x minus 30y equals 90. And the second one multiplied by 5. 5 times 3 is 15, so we got 15x. 5 times 6 is 30, so plus 30y. And 5 times 9 is 45. Add these together, we get negative 30y plus 30y right here cancels to be 0. So we've eliminated the y's. 24x plus 15x is 39x. 90 plus 45 is 135. Divide by 39, we get x is 135 over 39, which reduces to 14/13. Similar, we can eliminate the x's. Multiply equation 1 by 3 and equation 2 by negative 4 is one way to do that. Multiplying the top one by 3 gives us 12x minus 15y equals 45. And the bottom one by negative 4 gives us negative 12x minus 24y equals negative 36. This time when we add the x's cancel and the y's are negative 39y equals 9. And divide both sides by negative 39, we get y equals negative 3/13. Again, the same answer we got before, so that's as good. Okay, so now what does Gauss-Jordan look like for this? Well, hopefully you did this. 3x plus 6y equals 9 becomes 369 across the first row. And the next one, 4, negative 5, 15, that's the second row. And of course, this one's not as long as the 3 by 3 system because it's smaller, you know. So we want to get a 1 in the first row. First row, first column. One way we can do that is multiply the first row by 1/3. So that gives us, first of all, the second row stays left alone, and the first row becomes 1, 2, and 3. Next, we want to eliminate below that, so we can multiply row 1 by negative 4 and add it to row 2. So row 1 is left alone. Negative 4 times 1 is negative 4 plus 4 is 0. Negative 4 times positive 2 is negative 8 plus negative 5 is negative 15. Negative 4 times 3 is negative 12 plus 15 is 3. Now multiply row 3 by negative 1/13 to get that to be a 1. Notice that leaves row 1 alone, and it's not going to change this 0. Changes that into a 1, and 3 times negative 1/13 is negative 3/13. Finally, change that 2 into a 0 by multiplying row 2 by negative 2 and add to row 1. Leaves row 2 alone. So negative 2 times 0 is 0 plus 1 is 1. That's good news. We want that left alone. Negative 2 times 1 is negative 2 plus 2 is 0. That's what we wanted. And let's see what we've got to deal with here. Negative 2 times negative 3/13 is 6/13 plus 3. 3 is 39/13. 39/13 plus 6/13 is 45/13. So now we see x equals 45/13 and y equals negative 3/13, which is our answer there. Alright, so if we sort of do the standard order of steps in Gauss-Jordan, the way I've been telling you to go at these, what would be the next step? Label the step and do the next step. Don't solve the whole thing down to reduced row echelon form. Just do what would be the appropriate next step in the process. Go ahead and do this now. Press pause. Well, let's see. The order of the steps is we want a 1 in the upper left. Check. Done. We want zeros below it. Done. Next, we want to come down to the next column and the next row down, try to get a 1 there. Done. But next is once we get that 1, we want a 0 below it. That's what we need to do. We need to eliminate this. So we need elimination step. How are we going to do that? Well, use the one that's in that column, the leading one, and that'll do it without messing the zeros up over here. So we want to multiply our equation 2 by negative 3 and add to equation 3. So it's row 3 minus 3 times row 2. So it leaves row 1 and 2 alone. Let's do it. Negative 3 times 0 is 0 plus 0 is 0. Negative 3 times 1 is negative 3 plus 3 is 0. Negative 3 times 15 is negative 15 plus 1 is negative 14. Negative 3 times 7 is negative 21 plus 2 is negative 19. And that's what we wanted at that particular step. Do the same thing here. What's the next step here? Figure out what the next step's going to be. to be heading towards the reduced row echelon form and perform that step to get our next goal accomplished. Press pause now. What we want to do here is, well, let's see. We've got to get a 1 here. Done. 0's below. Done. We want a 1 here. Oh, it's not a 1. What do we want? We want to find a 1 below that. If it's okay, well, we want to just swap that up. So this is where we're going to do a row swap. And then the next step after that would be multiplying the row 2 by 1/3. So our goal to get a 1 there. Alright, let's do another one. What's next? Well, let's see. We got a 1 here. 0's below. Done. Down the diagonal, 1. 0's below. Done. Down the diagonal, 1. Nothing below it. Next step, go back and turn these 3 guys into zeros. I usually start with this one right here, but it really doesn't matter. You can change any one of these 3 to zeros. So if we change the 4 to 0, we use our elimination step, row 1 minus 4 times row 2. Notice this only changes row 1, so row 2 and row 3 are left alone. Negative 4 times 0 is 0 plus 1 is 1. Negative 4 times 1 is negative 4 plus 4 is 0. That's what we wanted to happen. We want that to 0 without messing that 1 up. Negative 4 times 5 is negative 20 plus 1 is negative 19. Negative 4 times 3 is negative 12 plus 5 is negative 7. Alright, one more. What do we do next? One here, already done. 0's below, done. 1 right where that 2 is. Well, normally we just multiply this by 1/2. 1/2 times 0 is 0. 1/2 times 2 is 1. 1/2 times 5 is 5 halves. 1/2 times 7 is 7 halves. And the other things in row 1 and 3 are left alone. Now, this does introduce fractions, and I mentioned you could apply some sort of clever techniques. If you're careful, we can put in 2 steps here and avoid fractions by doing this. We notice that these are already just 1 apart, so I could do a row swap. Well, a couple of ways I could do it. I could swap these 2 and then subtract row 2 from row 3 and then do a row swap. That's one way we could do it. Or I can do it this way. I can take row 2 minus row 3, it's going to put it a negative 1, and then just change the signs. So, well, that's what I did here. I left row 1 alone and row 3 alone, and say, subtract here. 0 minus 0 is 0. 2 minus 3 is negative 1. 5 minus 1 is 4. 7 minus 2 is 5. And then multiply this by negative 1, and which changed all the signs in row 2, and it left us with no fractions. So if you're careful about it and clever about it, sometimes it actually makes more steps, but then I've got less fraction arithmetic to deal with a little bit later on down the line. If you're doing it complete without a calculator, that might be something that's useful. Like I said, another way to do it would be take row 3 minus row 2, change row 3 to be a 1 right here, but then you just do a row swap. So we would actually end up with the same thing in row 2, but now instead of this in row 3, that way would end up with what we have in row 2 down here in row 3. Either way would work. Or you can just do the standard, multiply by half. Alright, now it's time for you to try one where we do the Gauss-Jordan technique, and we want to eliminate, we want to do this Gauss-Jordan elimination, and it's a 3-equation, 3 unknown system. Do the entire steps all the way down, and be sure you label your steps. This will take a few minutes, so you want to be sure to press pause, work it out, and then come back and check your answers. Very important you try this yourself. Okay, press pause now. Alright, here's the whole thing worked out. First we write it as a matrix, 2, 4, 6, 10, 5, 10, 4, 3, 3, 8, 13, 21. First order of business is get a 1 in the upper left-hand corner. One way to do that is multiply by 1/2. So if I multiply everything by 1/2, I get that to be a 1. Turns out all those numbers are even numbers, so good, no fractions. That's even a bonus. So 1, 2, 3, 5. Next, I clear out zeros below that. Use my leading 1 to do that. Is one way to do it. Now I do have other options. For example, to get this 5 to be a 0, I could multiply this 3 by negative 5/3 and add. But they're going to have some fraction arithmetic to deal that way. It's going to be easier if I use this 1. Okay, so for example, I'm going to change row 2. So I'm going to leave row 1 and 3 alone. So just recopy those. And take row 2 minus 5 times row 1. So take row 1 times negative 5 and add. So negative 5 times 1 is negative 5 plus 5 is 0. Negative 5 times 2 is negative 10 plus 10 is 0. Negative 5 times 3 is negative 15 plus 4 is negative 11. And negative 5 times 5 is negative 25 plus 3 is negative 22. Next, get a 0 below all the way down. So we need a 0 where the 3 is. Use row 1. So row 3 minus 3 times row 1. Notice row 1 and row 2 are left alone. So we're not actually changing row 1, just row 3. Negative 3 times 1 is negative 3 plus 3 is 0. Negative 3 times 2 is negative 6 plus 8 is 2. Negative 3 times 3 is negative 9 plus 13 is 4. Negative 3 times 5 is 15 plus 21 is 6. Next, so let's see what we've done. 1 here, zeros below here and here. Next, we want to get a 1 right here in the 2, entry. Well, it's a 0. That's when you want to do a row swap. Look below, swap these 2 rows. That's what we did here. Next, change that to a 1 by multiplying this row by 1/2. So that's 0, 1, 2, 3. So we got a 1 here, 0's below, 1, 0 below. Now the next thing is get a 1 right here. Multiply row 3 by its reciprocal, negative 1/11 times row 3. So we're dividing everything in this row by negative 11. That's 0, 0, 1, 2. So now we know z is 2. Go back and get zeros above. I usually do this one, then this one, then this one. But you can do them in another order if it's better for you. So I'm going to take row 1 minus 2 times row 2. Negative 2 times 0 is 0 plus 1 is 1. That's good. It's supposed to stay a 1. Negative 2 times 1 is negative 2 plus 2 is 0. That's what we wanted to accomplish. Get that a 0 without messing that 1 up. Okay, what does it do to the rest? Negative 2 times 2 is negative 4 plus 3 is negative 1. Negative 2 times 3 is negative 6 plus 5, which is also negative 1. Get a 0 here. I'm going to use the 1 leading 1 below it, which is that 1 down here. So I'm going to I'm just going to add row 3 to row 1. So I'm leaving row 3 and row 2 alone. I'm changing row 1. 0 plus 1 is 1. 0 plus 0 is 0. 1 plus negative 1 is 0. That's what we wanted. We wanted this is 0 without messing up this 1 and 0. Now what else do we have? Well, we have 2 plus negative 1, which is 1. And finally, we get that 2 to be a 0. Oh, back. We get that 2 to be a 0 by saying row 2 minus 2 times row 3. So it leaves row 1 and 3 alone. Negative 2 times row 3 and add it to row 2. So negative 2 times 0 is 0 plus 0 is 0. Negative 2 times 0 is 0 plus 1 is 1. Negative 2 times 1 is negative 2 plus 2 is 0. And what else do we have? Negative 2 times 2 is negative 4 plus 3 is negative 1. And now we have just what we want here. One's down the diagonal. Lower triangle 0, upper triangle 0. So now we just have x is 1, y is negative 1, z is 2. So our answer is x, y, z equals 1, negative 1, 2. And I did a calculator check here, but you can certainly check them by hand. I can just check them in my head here pretty quickly too. 2 times 1 is 2. That's 4 times negative is negative 4. So 2 plus negative 4 is negative 2. 2 times 6 is 12 plus negative 2 is 10. So it checks there. And similarly, I can check it in my calculator this way. 1 store x, negative 1 store y, 2 store z. And then type in the left side of the equations, and the output should be the right side of the equations. So it did check. Please be sure to check your answers. It is so easy to make a mistake here. So easy. So be sure that you check it. Also, one reason why it's really good to label them. If you do make a mistake, if you don't label them, you're going to have an almost impossible time trying to find your mistake. But if you label things, you can remember what it is you said you were going to do. You can see if you did it correctly. Alright, here's another one for practice. Solve this system with the Gauss-Jordan method. Be sure to label your steps. Go ahead and work this out now. Press pause. Alright, here we go. First, we want a 1 right here, so I'll multiply row 1 by a half. This is 1, 2, 3, and 5. Next, get zeros below with our elimination step. Negative 5 times row 1 plus row 2. Let's see, it's 0 here. Negative 5, negative 10 plus 10 is 0. Negative 3 times 5 is 15. Negative 15 plus 4 is negative 11. Negative 5 times positive 5 is negative 25 plus 3 is negative 22. Get a 0 below there. Negative 9 times row 1 plus row 3. So you leave row 1 and 2 alone. Negative 9 times 1 is negative 9 plus 9 is 0. Negative 9 times 2 is negative 18 plus 18 is 0. Negative 9 times 3 is negative 27 plus 16 is negative 11. Negative 9 times 5 is negative 45 plus negative 9 times 5 is negative 45 plus 5 is negative 40. Some error there. Okay, we still going to be the same conclusion, because the next step what I want to do is take, I want to show you, I want to eliminate, these are already set up to do elimination, so if I just do row 3 minus row 2, it's not necessarily normally the next step I would do, but I'm going to go ahead and do it because they're so nice here. And I subtract, these are still zeros, that's a 0, and I subtract row 2, so it's negative 40 plus 22, which is negative 18. Yes. Okay, so we fix that. Okay, but now look at the last one. The last equation now says 0x plus 0y plus 0z equals negative 18. Or, in other words, 0 equals negative 18. Which is a false statement. It's always a false statement. Okay? Well, if you get a statement that's always false, that means you've reached a contradiction. So there are no solutions. The only ordered triples that make this work are the ones that make 0 equal to negative 18. There is no such thing. So anytime we get a row that's all zeros except for the last one on the right, then we have 0 equals and something non-zero. That's a contradiction, and so that will be no solution. That's what we call an inconsistent system. We can stop right there. We don't have, it's not quite in reduced row echelon form, but we don't need it to be there. We can stop now and just be done. To get it in reduced row echelon form, we need to turn the negative 11 into a 1. We turn the negative 18 to a 1, and we clear out zeros above those. But you'd still have 0, 0, 0, 1, which is no solution. And you'd have 1, 2, 0, 0. Inconsistent system. No solution. Alright, try this one. Another one for more practice. Press pause, work this out, come back. Well, hopefully you're back now after you've tried this yourself. Takes a little while to do this. Okay, it's just a long process. But the matrix helps kind of keep it organized. So the first thing I want to do is write it as a matrix. 2, negative 2, 4, 6, 3, 7, negative 5, 3, negative 3, 9, 1, 7, 15. We want a 1 in the upper left-hand corner, so we multiply everything in that row by 1/2. Turns it into 1, negative 1, 2, and 3, with the second and third rows left alone. Next, get a 0 below that. That's our elimination step. So we're going to turn that 3 into a 0. So we're going to leave 1 and 3 alone, and we're only going to change row 2. So we're going to use row 1 to do it with. So we're going to take row 1 times negative 3 and add here. Okay? Now notice there is something else I could have done. Eventually in the next step I want a 0 down here where the 9 is. Since 9 is a multiple of 3, I could multiply row 2 by negative 3 and add to row 3. That would have given me some different numbers here, but it would have given me a 0 down here where I wanted it. I could have done that first. But I'm going to do it in this sort of standard order, which is get the 0 here first. And I'm going to do it sort of the standard way, which is to use the 1 here. Alright, so negative 3, so first of all, we're leaving row 1 and 3 alone. So changing row 2 by adding negative 3 times row 1 to it. Negative 3 times 1 is negative 3 plus 3 is 0. Negative 3 times negative 1 is 3 plus 7 is 10. Negative 3 times 2 is negative 6 plus 5 is negative 11. Negative 3 times 3 is negative 9 plus negative 3 is negative 12. Now I get the 0 here by using row 1. Negative 9 times row 1 plus row 3. So row 1 and 2 are left alone. Negative 9 times 1 is negative 9 plus 9 is 0. Negative 9 times negative 1 is 9 plus 1 is 10. And I'll let you look this over yourself for the rest of it. I'm not going to announce everything. Now notice that row 3 and row 2 actually are exactly the same. So that if I take row 3 minus row 2, I clear out a whole row of zeros here. That's something interesting is happening. Does this mean we have an inconsistent system like last time? Well, no. The last equation says 0x plus 0y plus 0z equals 0. That just says 0 equals 0. That's not a contradiction. That's something that's always true. That's going to usually indicate that we have infinitely many solutions. Or it will, in any that you have from me, it will indicate that these are infinitely many solutions. So let's keep going with this. We want a 1 right here, so I'm going to multiply this by 1/10. Multiplying by a tenth is pretty easy in decimal form, so I just use decimals here. 0, 1, negative 1.1, and 1.2. I can use this 1 to clear out a 0 above by just adding row 1 to row 2. And now this is the last one is in reduced row echelon form. Now this, unfortunately, we can't read the solution off just like we did before. In fact, there's not just one solution. Actually, 1, negative 1.8, negative 1.2, and 0, that order triple is one solution. And if you check that, as I will on the next page, it does check, but that's not the only solution. There are actually infinitely many solutions here. Okay? So what we're saying is this system of equations where we have 3 planes is equivalent to this system of equation where we have 2 planes. And what do 2 planes intersect in? A line in space. And so we get infinitely many points all in a line in space. So let's write the equations down. The first one says x plus 0y plus 0.9z equals 1.8, or x plus 0.9z equals 1.8. The next equation says 0x plus 1y minus 1.1z equals negative 1.2. Or in other words, y minus 1.1z equals negative 1.2. And the last equation says 0 equals 0. So I'm going to solve everything in terms of z. Okay, so get x by itself here. X equals negative 0.9z plus 1.8. The second one says y equals 1.17z minus 1.2. And I'm going to take something that's always true, 0 equals 0, and replace it with something that's also equally always true in terms of z, that is, z equals z. And so this is what we call a set of parametric equations for the line. It gives everything in terms of one variable, namely z. Now if I write the solution set, then I could write it this way. It's not just one thing, so we have to say x, y, z, order triple is an element of some set, and that set looks like the x-coordinate is negative 0.9z plus 1.8, the y-coordinate is 1.1z minus 1.2, and the z-coordinate is z, such that z can be any real number we pick. So pick whatever z you want, plug in these formulas, and you can do y and x. So in this case, z is like the independent variable, and x and y are dependent on z. This is what we call a dependent system, and there are infinitely many solutions. And graphically, this is a line in three-dimensional space. Now, how do you go about checking one like this? Well, when you have one row of zeros, we should have a line, and so if we just get 2 points to check, it should check. So one I check is when z is 0, and that is, you can see x, y, and z are 1.8, negative 1.2, 0. And I also plugged in z equals 1 and worked this out. 1 times negative 0.9 plus 1.8 is positive 0.9. 1 times 1.1 minus 1.2 is negative 0.1, and of course z is 1. there's a typo there. This part's not supposed to be there. There we go. There we go. And I checked it using my calculator. So I took 1.8, stored it as x, negative 1.2 stored as y, and 0 stored as z. With that combination, I checked the equations. 2x minus 2y plus 4z is supposed to be 6. It is. 3x plus 7y minus 5z gives us negative 3. It's supposed to. 9x plus y plus 7z, sure enough, is 15. So that checks. But that's one we've gotten in the last column. But that's not the only one that works. This one here works too. And so I try it. 0.9 stores x, negative 0.1 stores y, and 1 stores z, and plug it in, and it works. And so we see that if we have points on that line, those 2 points work. They're on that line, and so the entire line is going to work too. If we wanted to be sure it's not the entire plane, that we don't have the same plane all 3 times, we should pick something else. Actually, maybe just keep the same x and y, but change the z to something else, and we'll see that we get a false statement on at least one, or not, maybe probably all 3 false. Okay, so this exercise, you have 4 matrices. Every one of these is already in reduced row echelon form. So let's assume we're still using our generic letters of x, y, and z for our variables, and write down the solution set to each of these 4 different sets of equations. So just write down and interpret your final answer, and tell me if the system of equations is dependent or independent, whether it's consistent or inconsistent. Tell me how many solutions you have, and then state those solutions in the solution set. Okay, 4 exercises to do here. Okay, these are not equivalent. These are 4 different sets of equations, 4 different answers. But they are all in reduced row echelon form. Okay, press pause and work this out now. Okay, the first one, notice the last line. It says 0 equals 1. That's not possible. So this is an inconsistent system. It is dependent, but it is inconsistent, and, well, actually just inconsistent is really the best word to use there. And it is a no solution case. Actually, I tell you what, let's do here. Let's don't call it dependent or independent if it's inconsistent. Let's just say it's inconsistent and leave it at that. Okay, so it's inconsistent, no solution, or the solution is the empty set, which is what this symbol means. The second one is our 1-point solution. One solution, which is 1 point in 3-dimensional space. X is 3, y is negative 1, z is 2. So x, y, z is 3, negative 1, positive 2. Typo. Next, we got a whole row of zeros. This is the harder one to write down. There are infinitely many solutions. The last row, since it's on the last row, that would be, so we got stuff with x's and y's here. Where we'd like to have a 1 for z, we don't have it there. So we replace that with 0 equals 0, replace that by z equals z, and so the last one is z equals z. This one says, the first one says x, 0y, minus 2z equals 5, so we can solve for x and get x equals 2z plus 5. This says y plus 4z equals negative 1, so y equals negative 4z plus negative 1. So we get that. So we get, here's our solution set. The order triple x, y, z is an element of the set 2z plus 5, comma, negative 4z minus 1, comma, z, such that z is a real number. This turns out to be infinitely many solutions that are actually in a line in space. This is a consistent system, but it is what we call dependent. So that third equation depends on the other two. Okay. So what happens here is there are infinitely many solutions, but that doesn't mean just anything works. Anything works for z, but once z is picked, it's your independent variable, the way we've got it set up, and then the x and y depend on the value of z. Okay, so the Gauss-Jordan technique basically sets it up where it's easier to solve in terms of z, so you let z be the independent variable. There also is a situation where you could get two complete rows of 0, which really means that you've got nothing but that first equation, which says x plus 2y minus z equals 3. And so you can solve for one of the variables in terms of the other two. Either solve for z in terms of x and y, or I'm going to do it x in terms of y and z. Because you already have the 1 here, it's sort of natural to solve for the x. So we get negative 2y plus z plus 3 is x, and then y and z can be anything. So when you get this situation where we have two independent variables, this actually is a plane, and there are infinitely many solutions. It's consistent and dependent. It's consistent because it has a solution, but not only does it have infinitely many, they're not even in a line here, they're actually in a plane. So y and z can both be anything they want, not even the same necessarily. They could be the same, it could be different, it could be anything they want for y and z, but then once y and z are picked, x depends on that. Alright, I got to do it once. Okay, here's a 4x4 system, variables w, x, y, and z in that order. Okay, let's use the Gauss-Jordan technique to solve this. Now here's where we start to really see some of the power of the Gauss-Jordan technique, because this starts to get really messy and harder to follow when you start to do it with just elimination without the matrices. But the matrices, it's just as easy as the 3x3 system or the 2x2 system. It's just longer. A lot more arithmetic. It's tedious, but it is something that's very doable. The parts that you do are quite easy to do. It's just tedious and very easy to make a mistake, but very straightforward to do. See if you can go ahead and do this now. Press pause. Okay, hopefully you tried this by yourself. And when you're done, here it is. Yeah, there's a lot of arithmetic here. It's just a big system. So here we have, notice we get 2, 2, negative 2, 4, negative 4 for the first row, 2, negative 3, 3, negative 1, 11, so forth. We get a 1 in the top by multiplying the first row by negative 1, by negative 1/2 to get a 1 here. Use that to clear out below. Row 2, to get a 0 there, we multiply row 1 by negative 2 and add the 2 to get a 0 there. You can see what it does to the rest. I'll let you study the handout carefully on your own, or just press pause and look at this carefully. Then we get a 0 here by multiplying the row 1 by 3 and adding to row 3. 0 below that by multiplying row 1 by negative 4 and adding to row 4. Next, we want to get a 1 here. I can multiply that row by negative 1/5. And luckily, I never run into any fraction arithmetic in this, which is pretty lucky because it can get nasty. Clear out zeros below that. Multiply row 2 by negative 4 and add to row 3. That's what I did here. Get a 0 down below that. Multiply row 2 by 2 and add to row 4. Next, I want to get a 1 here. So multiply this row by 1/3. Luckily, the row multiples of 3, so no fractions. Get a 0 below that, right there. Multiply row 3 by negative 2 and add to row 4. That's what that notation means. That's what we got here. Get a 1 here by dividing this row by 1. So, is that a contradiction? No, that one's just fine. That just says 0w plus 0x plus 0y plus 1z equals 0. In other words, z equals 0. That's fine. Continue on. Get a 0 here. Use this row, negative 1 times row 2 plus row 1. Get a 0 here. Oh, bonus, we already got a 0 there, so that was kind of fortuitous. Okay. Then get a 0, say, here next. So I'm going to use this row, positive 1 times this plus that. Clears out a 0 there. Now you got to get these two zeros. Use row 4 for that. Just subtract row 4 from row 1 to get a 0 there. subtract negative 2 times row 4 plus row 2 gives a 0 there, and then get a 0 there by taking row 3 minus row 4. And now we have our 1's down the diagonal, 0's here, and we get W is our first variable, so W is 1, X is negative 1, Y is 2, Z is 0, so W, X, Y, Z is 1, negative 1, 2, 0. Check it. I'm going to use a calculator. 1 stores W, negative 1 stores X, 2 stores Y, 0 stores Z. Hit enter after each one of those, of course. Then type in your equations. 2W plus 2X minus 2Y plus 4Z. Hit enter. It's negative 4. It's supposed to be negative 4. Type in 2W minus 3X plus 3Y minus Z and hit enter. And it's 11 as it's supposed to be. Type in negative 3W plus X plus 2Y plus Z. Enter and you get 0. And then finally type in 4W plus 2X plus 5Z. And sure enough it is 2. So that point does check. And what if I had 5 equations, 5 unknowns, or 15 equations, 15 unknowns? Well, it's not any harder, it's just longer. Okay? So it's just more of the same process over and over and over again. Okay? Now, one thing that you may notice about this is that this has a certain steps to it. In fact, there's one way you can always do it. I mean, you can always get a 1 here in the upper left-hand corner first. If this is a non-zero, multiply by its reciprocal. If it's 0, go down below it and find a row to swap. Then use that row to eliminate stuff below it. Then go down the next one on the diagonal. If it's non-zero, multiply that row by its reciprocal to make it a 1. If it's 0, find a row below to swap it and then continue. Once you get a 1, 0, use that row to 0 out below it. Go down the diagonal and keep doing this process over and over and over until you run out of rows. Then you've got a point where you've got 1's down the diagonal right here, last one in the third line. 1's down the diagonal, 0's in the lower triangle. Okay, that's actually called row echelon form. But we want reduced row echelon form, so now you use all these leading 1's to clear out above it. Use row 2 to make 0's above it. Use row 3 to make 0's above it, that leading 1. Use row 3 to clear out above, row 4 to clear out above. And so once we've done that, mission accomplished, we're at the end. This is a step-by-step process that is the same every time. Let's think about this a minute. Do we know of something that's really good about storing perhaps a large amount of data and applying a process that's the same over and over and over again? Well, hopefully you thought of computers or calculators. In fact, calculators and computers are very good at storing matrices like this, and they're very good at doing some manipulations. So, in our next video, we're going to talk about how to do some of these same things with a calculator. So the real beauty of this technique is not so much for doing it by hand, although it is useful for doing things by hand, particularly when you get up to 4 equations, 4 unknowns. Try that 4 equations, 4 unknowns thing by hand with just elimination, and you'll see the advantage of the Gauss-Jordan. But the real advantage of the Gauss-Jordan is once you see that you can write it this way, that gives you a method of coding it into a calculator program, and so you could program a calculator to do this process. So we're going to talk about that in our next video.